And welcome to this rather unusual scientific panel debate about the movie Frozen in Time by Kenneth Sorrento. Welcome to all of those who are joining us live here this Saturday evening, and welcome to all of those who are watching it at some later point on YouTube. Now, to all of those who are not watching us live, if you haven't yet seen the movie Frozen in Time on the CPH DOX, I think you should do so, because there will be a few spoilers here tonight. For those of you who haven't seen it, not a disaster. The things we will be talking about will make sense, or at least to try to make it do so. It's rather unusual that to have a debate like this, but CPH Docs has done a tremendous piece of work trying to set up everything and deserve a lot of praise for that. My name is Adam Hannestad. I'm a climate journalist on the Danish newspaper Politiken. I'm a former Greenland correspondent and a big Greenland and Arctic aficionado. So I have great pleasure in being joined today by three excellent guests for this first session, which will have us through about 25 minutes. I'm joined by Bo Møllesøe-Vinther, who is an associate professor at the Niels Bohr Instittutet of Copenhagen University, and the main character, perhaps, of the movie Frozen in Time. Eliza Cook, also of the Niels Bohr Institute, an assistant professor, and also one of the main characters in the film. She is an expert in volcanic ash, or at least you could say that part of this huge puzzle that climate science is. And our third guest, Christian Steen-Larsen, is with us from Bergen in Norway. He is a climate scientist at Bergen Universitet, and he has previous experience also being out on the ice in Greenland, but is right now dedicating his life to being a climate modeler. Now, first of all, this movie that you hopefully have seen or will see shows us how digging for ice cores in the middle of the Greenland ice, hundreds of meters down, can unravel mysteries that can be up to 100,000 years old. But I think the one thing I really would like to hear from you, Bo, first would be just working out there has got to be one of the most remote workplaces in the world. What's it like to work out there on the ice?
It is actually extremely comfortable. It maybe doesn't look that way, but you get used to the cold quite easily. And then we have a very nice camp, and it's a beautiful setting, of course, especially here in eastern Greenland, where we have all the mountains and it's a beautiful view. But other than that, it's of course hard work. We have to work a lot in order to get the ice core drilled within the short time window we have available where the weather is nice. So, but it's good, and it's of course close quarters, but we have a great team and
close quarters. Wait a minute. I've seen these images, and it's like this gigantic expanse of ice. Well, yeah. I mean, you can't ask for more workspace.
No, you're right, absolutely right. But of course, the living space that we have, that's small tents and so on. But you're right, it can't be called close quarters in the bigger picture.
What makes you pick this for a career?
This is that was a little bit random in it, I will have to say. That I actually wanted to be a meteorologist, and therefore I studied geophysics. But then I met these amazingly cool people at the University of Copenhagen who were drilling ice cores and looking back in time, and I decided I simply have to join this line of work.
Eliza, Bo has been out there many, many years now, and he's pretty much a veteran out there on the ice. But in the film, we see that you go there for the first time. What was it like? Was it like what you expected?
Yeah, actually, so I went. That was the first time in Renland, and I'd been to the Nîmes deep drilling camp once before that, a couple of years before that. So actually the two places were very, very different. For example, the Nîmes place was in the inland ice, so it was very, very remote, right in the middle of the Greenland ice sheet. Renland was on an ice cap, very close to the coast. So whereas in Nîmes that you'd have basically flat white all around you, in Renland you'd have these beautiful mountains in the distance. So visually, it was a really stunning place, and the flight in and out was just breathtaking. I don't think I've been to a more.
The way the two of you are talking about Rendon, I feel like visiting. I mean, it sounds like it's a tourist destination that's just waiting.
If you take a couple of inland flights in Iceland, and then a semi-charter flight to the East Coast, and then a DC3 ride, then you can get there in a couple of days probably.
Yeah, that DC3 ride there, it did look a little bit hairy, and in the film it's actually mentioned specifically that it can be quite dangerous. Does it feel dangerous when you're landing on the ice?
I think you're so exhilarated by where you're going, and you're so excited you don't really think about that too much, and you know that the pilots and the crew, they're really cautious, and they really check it out. So you're happy to put yourself in their hands really, and enjoy the ride, I guess. And it's being in an old retrofitted DC3 was a real experience, because it's an iconic plane.
Fitted with the wheels on skis so that it can land in rough terrain. It does sound pretty interesting, even though I have to say it's not just landing there that seems tricky, because obviously this work is very, very tricky. In the film, it's described that things can go badly wrong with the drilling itself. The drill can get stuck, the core can break. You've got to tell me, I mean, what's so bad about these cores breaking? Because what we're talking about, these gigantically long cylinders of ice that you're pulling out, what's the big problem if there's a crack in them? Oh, that's a question for you. Sorry, I should say.
It's the problem with having cracks in the core, if we have a lot of them. That is that then the samples that we want to measure, they get polluted. So it's very, very clean operation we have to do in order to get exactly the samples we want. And if there's any surface that is exposed to your hands or your fingers, or the air can come into it in some way, then there are a lot of measurements we can't do. So we really have to keep the core as intact as possible. Of course, we do have to break it in a few places, because that's the way we drill. So we drill 2 meters at a time, and then we pull up the drill and take these 2 meters of core up. And the way we do that is by breaking the core. Otherwise, we couldn't get it up. So some breaks we have to live with, but as few as possible.
Right, because obviously you can't have like a 500-meter long cylinder and transport that one back to Denmark. That would be a bit of a logistical nightmare. Even so, I mean, it seems one of the things that's explained here is that you can gather so much information, because these are, like, as it's described in the movie, tree rings that tell you a lot about climate in the last 100,000 years. Now, to me, it seems, when I watched the film, I was thinking, surely nature doesn't work as neatly as that. Sometimes there must be shifts in the ice that mean that the ice gets shifted around. It won't just be 100,000 years neatly on top of each other. How do you work around that?
The main thing we do is that we actually do a radar survey of the ice cap before we drill. And there we can see the layers inside the ice with the radar, and then pick the best possible site. But even though that we do that, then as we get near to the bedrock, near to the bottom of the ice cap, there will still be disturbances in the ice. And the best way we can check up on that is to compare what we see, like the volcanic layers in the ice, with other ice cores that we have drilled before, and then see if we have the same sequence, then it is unlikely to be disturbed.
So the more sequences you have, the more sure you are that the one you have is telling you exactly what you feel like knowing.
Exactly.
Eliza, when we're talking about these volcanic sediments, explain that to me, because that's your particular field of expertise. How can volcanic eruptions be used as markers?
So it's a very niche field, I have to say. But these volcanic events. So I look at the glass component of volcanic ash, which is called tephra, and it's very minute particles, like 0.01 of a millimeter, so like 10 microns across. And so when a volcanic eruption happens, these fine particles get thrown up into the troposphere and sometimes the stratosphere, and they can travel really wide distances. So I find in Greenland, for example, volcanic dust or ash all the way from Japan and Kamchatka, as well as mostly from Iceland, obviously due to its location. But the unique thing about these layers is that each geographical setting, say Iceland versus Kamchatka, the magma has a different geochemical fingerprint, just due to the fact that, for example, in Iceland, it's formed by ocean ridge spreading. In Kamchatka, for example, or Japan, it's subducted, so you've got crustal melt or oceanic crustal melt in the composition as well. So you've got these unique geochemical signatures of each of the eruptions that can then be used when you find different layers in the ice core records. You can get a composition of what the ash is sort of made of, and then compare that to different records. And then using this geochemistry, you can correlate the different records together. So I've looked at, say, different records from Greenland, for example, Neem, North Grip, as well as now Renland. And then we can correlate these sequences with different geochemical compositions of different ash layers from one ice core to the next. And then you know that you've got the same sequences between them. But another important thing is that you're also, we're looking very far back in time. So we're also building up a record of volcanic history from different regions. So you're looking at the frequency of specific volcanoes, such as those like Katla or Grimsvotn from Iceland, which might tell you a little bit about like the recurrence time of future eruptions. So that's also important to look at the past volcanic frequency of different.
But that makes sense. And there's one thing that I'd like to ask you, because in the movie it's mentioned that you have pretty good historical records from the Viking Age with specific dates of volcanic eruptions, and you can even find the same in, say, Greco-Roman times. But these are samples that go back 100,000 years. I mean, things weren't really written down back then. How can you use that as a marker?
No, for sure.
Oops.
So
I have to.
Yeah.
Oh, Eliza, we just lost you for a second, but you're back on.
Yeah, perfect.
Yeah.
So so we build up a chronology of volcanic eruptions back over time, and we can really use that for understanding volcanism in the past. As you say, in prehistory that isn't written down, and the main thing is that you can compare the well-dated ice core ages that we get from these different layers, and then if we try and find these same layers in different archives, such as marine sediment cores, that we then would like to compare to the ice cores to see what's going on in the atmosphere compared to the oceans. If we find the same volcanic eruptions with the same signature, for example, that's very close to a eruptive transition, we can see, do these are the mechanisms the same between the atmosphere and the oceans, based on this tie point at a very critical moment.
Right. So it's this whole puzzle of people working together in different fields to help each other find exact dates. For
sure. I mean, we actually wouldn't get that far in isolation. So we have a really nice community with the terrestrial paleoclimatologists as well as the marine paleoclimatologists, and we all share sort of our data, and we also work a lot. I mean, I do with igneous petrologists and geologists in different parts of the world that provide us with these reference materials from different volcanoes.
Thank you. That's. I want to get back to the ice and to Bo here, because now that we have a little bit of an idea, and I know that we barely scratched the surface of the science here, but now that we've got this slight idea of how you use these ice cores to get information out of the ice, there is, and I'm sorry to give a bit of a spoiler those who haven't seen the movie, but there is actually quite a bit of a potential scientific discovery towards the end of the movie. In that, again, spoiler alert here, we find that the ice that is further down could only have been deposited by winds from the Pacific and not from the Atlantic. Now, why, Bo, is that such a big discovery?
Yeah, so the main thing is that actually what we see here is a puzzle from all the Greenland ice cores. So the thing is that we see a signal in northwestern Greenland that we don't see in Greenland. So it's actually what we are not seeing that is the interesting part, but that's of course
Right.
a technical detail. But the idea is that that we, due to the fact that we have something in the northwest of Greenland, then the only real way that we can have it there and not on the other side of Greenland is if it came from that direction. So this is the main hypothesis here, that due to that fact that we have this difference across Greenland, then we hypothesize that this came from the northwest. This is still something that we work a lot on, because it's important if that's the case. Because if it was the case, then it means that the entire wind patterns during these climate periods that were in the ice age, where we had very huge climate change going on, that the wind patterns in the northern hemisphere changed completely, extremely fast.
And why is that important to us today?
The reason that's important is that we know that these changes, the big changes in climate in the past, were related to big changes in sea ice cover. And right now we are changing the sea ice cover in the Arctic. So what this means is that this sea ice change that we see in the Arctic has the potential to really change our average weather conditions and also the extremes by a lot. This is what this tells us.
Hans Christian, I would like to go to you, because although you have you know Bo, you know Eliza, you've been working with them at times, you have since moved to a different university and you're doing more, you could say, more general climate modeling. Given this information, is it as if this turns out to be the case, that the winds were able to penetrate this jet stream that normally locks off the Arctic Ocean, and the winds came up, that the wind patterns were completely different because of the sea ice cover, would that be a significant thing?
So the importance of this research question can really not be stressed enough. It is very important to understand where the water that falls as snow on the Greenland ice sheet comes from, because in the future we know the climate will change, and in order to understand how the Greenland ice sheet and the sea level in the future is going to react to that, we need to understand where the water comes from. So to illustrate how debated this question is, we can actually just see, just a month ago, a colleague of mine published a paper using a specific type of modeling, showing that today a lot of water vapor comes from the Pacific. But in my research group, my postdoc Anne-Katrine Faber is right now submitting a paper using a different methodology, showing that moisture for the Greenland ice sheet is coming much more locally from the Atlantic.
So, but why would it be important? Let me rephrase that. If there is a connection between the loss of sea ice in the central Arctic Ocean, would it be possible to make some assumptions based on the data that seems to be getting out of these ice cores on how the climate will react in the future?
So the holy grail for us as climate modelers is to understand the underlying physics of the climate, okay? And in order to do that, we use models. So with the data that Bo and his team here have produced, we can actually take these models and compare with the observations and see if we are capturing the underlying physics accurately enough. Because if we don't have models that are able to simulate the climate correctly, we cannot really trust them into the future.
What's the importance of having people out there in the field digging for ice cores or doing other work similar across the globe?
So again, it's kind of our way of ground truthing our models. Without somebody really dedicating their life to getting these data, we don't know if our models are actually accurate. And it's important to remember that climate change is happening. The Arctic is changing. It's going to affect atmospheric circulations, which is going to spill over to the whole northern hemisphere, causing changes in heat waves, cold spells, and we want to be able to predict this. And we need models to do that. And the observations from the field gives us this opportunity to test if we have the right physics and the right way of simulating the climate.
I love the idea of sitting here in the middle of something that actually looks like a potentially big scientific discovery that we're just waiting now to see whether your peers are accepting this as solid data. Bo, I know that you and your colleagues are writing a paper about it. How far are you from getting that published?
This is still some way off. So when we drill an ice core, then of course the first step is that we need to document very thoroughly the core and the chronology, so that is published, that we know that this core has more than 100,000 years of data worth in it. And then the next step we were looking at was that we looked at the sea ice signal, so that we can see, is the rapid climate changes, is it associated with sea ice? We can actually measure sea salts and so forth in the core and check, okay, the temperature signals we see, are they associated with the sea ice? And now the final step is, of course, this important discovery that we need to work on. But this is, I can say so much that it might actually be helped along by the situation being as it is, that we are now all working from home. So we might all be less distracted in these coming weeks.
I remember reading that in previous epidemics, quite a lot of scientific breakthroughs had been done. I think it was Newton formulating his theory of gravity because he had to sit and work from home during a pandemic, or at least an epidemic. So one can hope that something that is a good sign, specifically here. I have to say, right now it sounds like, Hans Christian, the modelers who are making these climate models to describe previous weather patterns and potentially future weather patterns, or climate patterns, I should say. And the field workers, the observers, the ones who are out on the ice, like Eliza and like Bo, are working beautifully together. Is that always the case?
I would say that there's been very, very big improvement over the last decade. There's, like, you can imagine, like, there's the community of scientists that go out, collect data, and then there's a community of scientists who run models. And it's not because we don't want to collaborate. We really want to collaborate, but we are having different scientific backgrounds and education. So we're also speaking different scientific languages sometimes. And that can probably be improved sometimes, and that's why, like, I have a background in observations, but now I'm running climate models, so I'm kind of like bridging the gap between these two groups of scientists, because we really need to merge climate models and observations to really get to the bottom of, like, really accurately understanding the physics of the climate.
So when some of the other modelers saying, "Oh, this is very interesting. Can you get me another ice core that is just next to a volcano?" And then you can say, "Actually, we can't do that. Maybe in 10 years if we start an expedition."
It's very much like that. Like, it's good to kind of, like, sometimes sit in discussion groups with modelers and remind them that, it does take several years, sometimes a decade, to get this data point. And it's something that should be treated with uttermost respect and not just be dismissed because it doesn't fit the model.
I'd say what you've been doing out there on the ice, it certainly seems impressive. And I would also say that as much as you make it sound like a 4-star hotel with beautiful views, it also does look like it's pretty hard work and pretty cold work. I mean, basically you're freezing your butts off, honestly. I'd like to ask Eliza, if you don't mind answering this for me. I was wondering, you and Bo and many others have been out there in the field so many times and digging up data, literally, and then turning them in for evaluation, using it. Other scientists have used it to get other data, and then climate modelers help you. And finally, you publish papers and you try to describe how climate change is happening and what might be the results to your best knowledge, only to have, well, I could name a few presidents, dismiss it as fake news and just scientists who are just inventing results just to pat each other on the back and make sure they have jobs tomorrow. How does that feel?
I mean, of course, it's disappointing when there is that reaction. But I think that science and politics have always had a difficult marriage, so to speak, especially when the results are at odds with maybe a political agenda or whatever. But the scientists are really passionate, and our jobs are pretty unstable, and we do it because we love the work, and we were sort of committed to finding out what might happen in the future. But of course, it's not fake news that, say, for example, by 2050 we're going to be almost 10 billion people around the globe, and climate science will be able to help inform lots of different key strategies, such as food production. We might have 50% more demand and a food gap. And in a context of a changing climate where we might not be able to sustain growth in some regions, we really need climate and climate scientists to help inform what might happen on our strategies going forward in the world.
Bo, just to round this off, this part of the debate, I would just like to hear you also. I mean, is there a slight hope in you that you and your team have found a bit of a puzzle that might make the world a little bit better or more informed?
Yeah, I actually have a lot of hope that it is trending in the right direction. So and as odd as it can seem, then if I have to see anything promising in the situation we are in now with the global pandemic, it is that it shows everybody that we are on this earth together, and it seems that we are actually willing to take rather dramatic action in order to improve our life and our way here in this globe, and we can work together quite nicely. So I think all this willingness and the global awareness could very well spill over into the climate change policies as well.
That's a very beautiful hope, and I do hope that you're right. I would like now to change channels a little bit, because we have two more guests tonight, and who will be talking a little bit more about the policy side and the strategy side of climate change, of the whole climate change debate. So we'll be building on top of what we've just been talking about and of the results of the movie. But for now, I would like to say thank you very much for coming to our three excellent guests. Really a pleasure to have you through, and best of luck with your work.
Thank you very much.
Thank you. Goodbye.
And for everybody else, stay tuned. I will just change channel. There'll be just a short blip, and then I should be able to get back on again with our next two guests. And we're back again with the second part of tonight's debate on the climate change, based on the movie Frozen in Time by Kenneth Sorrento. And it is not necessary to have seen the film to watch this. We have just spoken to three people working with climate science, and we're now moving a little bit more into the policy section. Joining me here now are Sandra Cassotta, who is an associate professor in international, environmental and energy law at Aalborg University, and Jarl Krausing, who is the head of international operations at the Danish think tank Concito, which works with the green agenda, climate change and environmentalism. Thank you very much for joining me, both of you, for tonight's debate. There are some people who will be watching this live, others will be joining us later. And again, I should say, if you haven't seen the film yet, Frozen in Time by Kenneth Sorrento, it is absolutely worth it. So definitely log in to see it afterwards. Now, two of you, we have just been speaking to climate scientists who do have a bit of a frustration that sometimes they work hard to find information, turn it into good climate science, and then only to have it dismissed by at least some politicians around the globe who are hesitant to accept the realities of climate change. Sandra, you were the lead author of the IPCC, the UN Climate Panel report on oceans and the cryosphere, or more colloquially, water and ice. So you've been working a lot with shaping the agenda. I don't want you to get too political because that would only put you in trouble with the IPCC. But overall, is it your opinion that the public understands just how much the Arctic means for global climate?
Yes, I've been lead author on this report, Ocean and Cryosphere, and the main task was not really to shape the agenda, but to make an assessment of the current literature on cascading effect and interaction between physical world, biochemical physical world changes, ecosystem, and the human aspects, human responses. So my part, since I'm a legal scholar, environmental legal scholar, was focusing on the human responses and the responses in international law, governance to the physical interaction and the cascading effects. So, and we have been focusing on the Arctic, starting from the scientific aspects to understand what is happening there, because we know that ice is melting, but what does it mean that our ice is melting? It means that it is retreating. In the year 70s, we had in the Arctic Ocean a lot of ice. From the 70s.
So you mean the ice edges, or the edge of the ice in the central Arctic Ocean,
yes,
and the glaciers, they're retreating.
Retreating. And from 70s to 2012, there is 50% of ice coverage less, which is really dramatic. And from 2012, these are studies conducted by NASA, by scientific studies, it will get worse, according to predictions. So this means that we have lost 80% of the multi-year ice, and it is really dramatic. So, and this means also that the thickness of ice, it is getting thinner, so it's easy to drill. This means a more accessible Arctic Ocean. So it means that the Arctic Ocean will have availability of huge potential of access to petroleum, for example, competition between states to get access to these new resources in the high seas, more mining opportunities, new trade routes, new shipping routes, for example, connecting Europe and Asia with the North-East Passage, so you can actually get shorter by avoiding the Suez Canal. So all this means more activity, more risks, and in that sense. And the thing is that what is going on in the Arctic is not only a problem in the Arctic, but also from the Arctic to the rest of the world. Like if we look at the Arctic a little bit like a refrigerator of the planet, you open the door and all the planet will feel the consequence. And I'm referring.
This is what we saw in America actually last year, when suddenly you had this tremendously cold winter, and it was one of the images that was being used was that it's sort of like keeping the refrigerator door to the Arctic open. because these jet streams were breaking, the ones that encircled the North Pole.
Yes, and I'm referring more to the open Arctic ocean waters, because they absorb the heat, and all this heat is not going away. It will stay there, and it will stay there even if when the ocean Arctic will try to freeze, and it will accelerate and amplify the effect of climate impact in the world, in the planet. So the question is, are we prepared from an international law perspective to do something in international law and governance to this? Because this is a new link, a new impact, a new nexus between climate change and law of the sea and the sea. So can the law catch up with this new nexus, these new interactions? And we have, it's not that we don't have anything. We have a big convention of the law of the sea, the United Nations Convention of the Law of the Sea, UNCLOS. We have the UNFCCC Convention, United Nations Convention, Framework Convention on Climate Change. We have the Paris Agreement. We have these two main things, but they need to be connected and they need to interact, and we need more instruments to implement. We need strategies to make the connection between, because currently the capacity of international law and governance to cover these new interaction that are happening is not enough to tackle the rapidity of the change, the non-linearity of climate change, and several issues. So we really need in the future to improve this capacity to regulate these new interactions that we didn't know before, because at the time when UNCLOS was written, they didn't know a lot about climate impact in the water.
No, obviously, and I'm sorry to interrupt you, but it's sort of like what you're explaining really is how what's happening in the Arctic unlocks a whole new series of new issues.
Absolutely.
Shipping, fisheries, geopolitics, mining. It's not just ice melting into the water and raising the oceans. Now, in this film, we're actually shown that if these theories that the researchers are showing in the film are correct, then it shows that changes in these weather patterns, these climate patterns in the Arctic can take place even faster than was previously accepted. So it could get even more serious. Jarl, I would like to turn to you also, because you work with shaping international opinion. And of course, that sounds fairly large, but that is your job. You are an advocate of the climate. Is it your opinion that governments across the globe are really understanding that this is serious and it can go really fast?
I mean, on one hand, you can say that the governments, they did manage to exactly force the Paris Agreement, and in that sense, adopt a common agenda, and also, a commitment to act on the issue. The thing is, it's just too little and it's too late. And I think part of the really reason is that you're competing with a lot of other policy priorities, but also vested interest. In order for us to decarbonize the world, which really is what this is all about, so we avoid emitting greenhouse gas into the atmosphere, it really goes counter to a lot of the existing economic system we have in the world. So apart from this being complex issues to communicate, it's also coming into a political landscape where you really have a lot of different interests that are not at all necessarily actually wanting to appreciate the real issue. And I think there's another aspect which is important to pull out here, which is climate change being perceived as a clear and present danger?
Is it?
Well, for many, it's not. You just have to compare how the world has been reacting to the coronavirus. Now, there you can see very clear attribution to what cause and effect is. You can measure, on the street, you can see the impacts. But on climate change, you actually have to go through a couple of iterations before you actually understand what science is saying to the reality that you are facing as a citizen or as a government that you need to act on. And in my experience, it really is a challenge for the political level to actually just understand what is at stake and what science is actually trying to communicate. Models are being produced and put on the table to provide guidance for policymakers, but still you have several models that point to different scenarios, and that alone opens up an array of interpretation by politicians or vested interest, if you would say so. So I think sorry.
No, I was wondering if I can ask you, because when you work your advocacy, when you talk to politicians, which I know that you do a lot, I'm sure you don't just pull up a scientific report and slam it on the table and see there, people, it's black on white. We've just seen how some researchers are finding specific corners of the puzzle by digging up ice from Greenland and analyzing it. This then is compiled into other reports, goes to people like Sandra, who compile these reports into huge mega reports from the United Nations. How do you work with those, Jarl, when you talk to the politicians? How do you use the scientific reports in this sense?
Each of the political parties, they have spokespersons that are responsible for the climate agenda. But some of these spokespersons are also responsible for 10, 15, sometimes even more issues than just climate change. But it is important for us to engage with those spokespersons from the parties that are in parliament and basically educate them on the issue, engage in the dialogues with them. And we do that either directly, individually, or we do it together with partners. And there we just have to also come to terms with the fact that when you look at politicians, they are as, diverse as everybody else you meet.
I thought you were going to say stupid, but okay, yeah.
Well, no, but I mean, these are complex issues. And I think another challenge that I've run into personally several times is we have this tendency of talking about a climate that is changing and what will the world look like in the year 2100. Okay, politicians can kind of understand that timescale, but if we try and then say, okay, but you actually also need to take upon, the long-term lens, what will happen with sea level rise or storm surges, weather patterns on the longer timescale. That's where you actually see what are the fundamental threats to a country like Denmark. And politicians simply cannot relate to timescales that are too far away from them, or to issues that are too complex or perceived as being too detached from their need to take everyday decisions or policy development processes, etc. So that is a challenge. What I think has been really interesting over the last couple of years has been the learning that for many years we have been thinking we needed to communicate, math, graphs, megatons, curves, all these kind of scientific materials to educate the politicians and the broader public, etc. But what has really made the public push politicians to change over the last few years have been, well, yes, basing on science, but actually putting on a layer of value. We want, you have a young generation that is afraid of the future and they're demanding change. They're informed by science, but politicians are now acting because they have science plus, value-driven kind of demands for change, which I think it's also opening up a new window on how we can use science to push politicians to act as they should do.
There's one thing I would like to just end this on, because Sandra, I know that apart from being an expert in environmental law, you also have a specific interest not just in the Arctic, but also of climatically displaced people. We don't have a lot of time yet, but you mentioned that what happens in the Arctic doesn't stay in the Arctic.
Exactly.
Why should we be worried about something happening in the Arctic, meaning climatically displaced people in Central Africa?
Well, in Central Africa, first I will start that this could, because of the global dimension of climate impact in the polar, we will have, this is proof scientifically that there is sea level rise. And if there is a sea level rise, it is clear that this is going to impact the people who are living in the Pacific because of the sea level rise. For example, small islands and developing states that will become totally impossible. It will become totally impossible to live there. So they will be obliged to flee, to move. And this will be actually big because it will be a massive, much more movement, more bigger than the normal refugee movement in the future. So what I think is that also this problem of the sea level rise interacting with the anthropogenic effects of natural resources extraction and the plan of big oil company in the Arctic to drill from here until 2030, these two interactions may really be so serious that we will face scenarios that we can simply not imagine.
I'm sorry to break you off because we're getting extremely close to the deadline.
Yes.
It's just it fascinates me deeply to find that these cores, these bits of history from tens of thousands of years ago in the Greenland ice have a bearing on what kind of scenario we should expect in the next 20, 30, 40 years.
But to answer your question about East Africa, just think about the consequence of climate change and predictability, that we don't know what will happen, where and how many will flee, and which event will determine the movement of people. About what happened for the crisis in East Africa of the invasion of these locusts, these insects, that have destroyed and devoured entire crops and pastures, and because of the fact that the climate has changed and the abrupt changes and the frequent precipitation and change of temperature that make that the eggs of this insect have broken. So this will determine a huge, massive movement of people.
And what you're saying is that we should all be prepared to make the link inside our head.
Exactly.
That what is happening in one part of the globe that had a direct implication maybe later in another part of the globe, which is truly a fascinating concept, because it means also we're not looking over time, but also across the planet. This is all that we have time for tonight. I'm sorry we could have gone on much longer, I'm sure, but thank you very much to both of you for being part of this debate. Thank you so much, and I do hope to all the people who have been able to sit through all of this, I hope you have learned something. I certainly have. And again, if you haven't seen the movie Frozen in Time by Kenneth Sorrento yet, make sure you do. It is certainly worth the fairly small price you'll have to pay to see it. Thank you very much again to Sandra Cassotta and to Jarl Krausing. Thank you very much from me.
Thank you.
And have a very pleasant evening.
You too. Thank you.